Welcome to Triune Biblical University Global Extension USA channel. A warm welcome to all our returning subscribers and a heartfelt greeting to our new viewers. We're so glad to have you with us today. Whether you've been following us for a while or are just joining the community, we're excited to embark on this learning journey together. At Triune Biblical University Global Extension USA, we strive to provide valuable educational content that empowers you to grow, learn, and succeed. Your continued support and participation mean the world to us. In today's session, we are diving into lecture topic, where we'll explore important concepts and provide practical knowledge that you can apply in real-world scenarios. This lecture is designed to challenge your thinking and deepen your understanding, whether you're a beginner or an advanced learner. Thank you for joining us, and we hope you find today's lecture both insightful and inspiring. Let's get started. Chapter 4: Advanced Soil Mechanics and Constitutive Models. For Point 1, Stress-Strain Relationships in Soils. The relationship between stress and strain in soils is a fundamental concept in soil mechanics, as it governs the soil's response to external loads, such as those imposed by foundations, structures, or other geotechnical applications. Understanding these relationships is essential for predicting soil behavior under different loading conditions and for designing safe and efficient structures. Stress-strain relationships in soils are typically nonlinear and depend on several factors, including the type of soil, moisture content, loading rate, and environmental conditions. This section explores the key concepts, models, and behaviors associated with stress strain relationships in soils, highlighting the advanced theories and approaches used to describe these relationships in more complex or challenging geotechnical problems. For Point 1.1, Basic Stress-Strain Behavior of Soils. At the simplest level, the stress-strain relationship can be described using basic elastic theory, where strain is proportional to stress. However, for soils, this relationship is often much more complicated due to the heterogeneous nature of soil, its granular structure, and its ability to exhibit both elastic and plastic behavior. Key points of the basic stress-strain relationship for soils include elastic behavior. Initially, soils can exhibit elastic behavior, meaning that when stress is applied, the strain increases proportionally to the stress. When the stress is removed, the soil returns to its original state. Plastic behavior. Beyond a certain threshold, called the yield point, soils may exhibit plastic behavior, where deformation becomes irreversible and the soil does not return to its original state after the stress is removed. Yielding and hardening. In many soils, after initial yielding, the stress-strain relationship can continue to evolve, often showing signs of hardening or softening, depending on factors like soil type, compaction, and external loading conditions. The initial elastic response is generally described using the Young's modulus E, while the Non-elastic behavior is captured by DRENT models that describe plasticity and hardening. For 1.2 soil behavior under DRENT loading conditions. Soil behavior under loading conditions can vary significantly depending on the type of loading and the soil's characteristics. Common loading conditions include compression. When a soil is subjected to compressive forces, it experiences a reduction in volume, which is generally accompanied by an increase in stress. In cohesive soils, compressive behavior can include both elastic and plastic deformations, while in granular soils, like sands, the behavior is typically more dominated by elastic compression. Shear stresses cause a soil to deform in a way that distorts its internal structure. The relationship between shear stress and shear strain is a key determinant of the soil's shear strength, which is crucial for stability analysis in geotechnical engineering. Cohesion and friction within the soil play a major role in this behavior. Triaxial loading. When soils are subjected to stress in 3 dimensions, as in the case of triaxial tests, the stress-strain relationship is influenced by both the confining pressure and the applied axial stress. This type of loading helps to understand how soils behave under more realistic, complex conditions found in real-world structures like foundations or embankments. For 1.3 nonlinear stress-strain behavior. One of the key challenges in understanding soil behavior is the nonlinear nature of the stress-strain relationship. In contrast to materials like metals, which exhibit linear elastic behavior up to a point, soils often show a curvilinear stress-strain relationship. This is particularly evident when analyzing the response of soils under large strains or during failure. Nonlinear behavior in soils is influenced by factors such as soil type and composition. Granular soils, like sand and gravel, often exhibit a DRENT nonlinear behavior compared to cohesive soils, like clay, which may show more pronounced plastic behavior. Moisture content. The moisture content significantly affects the stress-strain behavior, particularly in fine-grained soils. Higher moisture content can lead to reduced friction and altered soil strength. Strain rate. The speed at which stress is applied can influence the material response. Soils may behave differently under rapid loading, dynamic versus slow static loading. The stress-strain curve for soils typically shows the following phases. Elastic region. In the initial part of the curve, the soil deforms elastically, meaning the deformation is recoverable upon unloading. Yield point. Beyond a certain stress level, the soil reaches the yield point, where plastic deformations begin, and the soil starts to undergo permanent strain. Post-yield behavior. After yielding, the curve may show strain hardening increase in steepness or strain softening, decrease in steepness, depending on the soil type. and the specific loading conditions. For point 1.4 key parameters in stress-strain relationships. Several important parameters characterize the stress-strain relationship of soils, which are crucial for modeling and understanding soil behavior under load. Young's modulus, a measure of the steepness of soil in the elastic region. It represents the ratio of stress to strain in the linear portion of the stress-strain curve, and is essential for understanding soil deformation in response to loading. Poisson's ratio, a measure of the lateral strain deformation perpendicular to the applied load to the axial strain. This parameter is used in understanding the volumetric change and deformation behavior of soils under load. Shear modulus, the ratio of shear stress to shear strain in the elastic region. It is particularly important for understanding the behavior of soils subjected to shear forces, such as in shear strength analysis. Yield stress, the point at which the soil transitions from elastic to plastic behavior. It represents the maximum stress the soil can withstand without experiencing permanent deformation. Plasticity index, PI in fine-grained soils, like clays, the plasticity index, which is the difference between the liquid limit, LL, and plastic limit, PL, influences the stress-strain behavior. Higher plasticity can result in more pronounced plastic deformations under loading. For 1.5 constitutive models for stress-strain behavior in soils. To represent the complex stress-strain relationships in soils, several constitutive models have been developed. These models aim to describe the nonlinear and time-dependent behavior of soils under different loading conditions. Some of the most common constitutive models for soil stress-strain behavior include linear elastic model. In this simple model, soil is assumed to behave elastically under all loading conditions. This model is most appropriate for small strains and situations where soil behavior remains in the elastic range. Mohr-Coulomb model. This model is widely used to describe shear failure in soils. It relates the shear strength of a soil to its cohesion and the angle of internal friction. The Mohr-Coulomb failure criterion is typically used for cohesionless and cohesive soils in situations of large shear deformation. Kamklay model. The Kamklay model is often used to describe the behavior of overconsolidated clays, where the soil undergoes both elastic and plastic deformations. This model incorporates the effects of plastic flow and is especially useful for understanding soil behavior under consolidation and loading. Modified Kamklay model. A variant of the Kamklay model, the modified Kamklay model is used for soils that exhibit both volumetric and shear strain, making it suitable for describing the stress-strain behavior of clays under varying stress states. Hardening soil model. This is a more advanced model used for both cohesive and cohesionless soils. It accounts for the hardening and softening behavior of soils. Underloading, making it useful for complex geotechnical problems such as foundation design and earthquake engineering. Hypoplastic models. These models extend classical plasticity theory to describe the behavior of soils over a broader range of loading conditions. They are particularly useful for simulating the behavior of granular soils and soils under dynamic loading. For 1.6 application of stress-strain models in geotechnical design. Understanding and applying stress-strain relationships is critical for several areas of geotechnical design. Foundation design. The stress-strain behavior of soils helps in determining the bearing capacity of foundations and understanding the potential for settlement and differential settlement. Slope stability analysis. The shear strength parameters and stress-strain behavior are vital for evaluating the potential for slope failure in cohesive and granular soils. Earthquake engineering. Soil response under cyclic loading, as described by stress-strain models, is crucial for assessing liquefaction potential and designing foundations and earth-retaining structures to resist seismic forces. Soil structure interaction in structures like tall buildings or bridges. Understanding the stress-strain relationship between soil and structure is essential for ensuring long-term stability and performance. For 1.7 summary. Stress-strain relationships in soils are complex and influenced by factors such as soil type, moisture content, loading conditions, and strain rate. While basic elastic models may suffice for simple cases, advanced constitutive models are required to capture the nonlinear and time-dependent behavior of soils in more complex geotechnical problems. Understanding these relationships is essential for predicting soil performance under load, designing stable foundations, and mitigating risks related to soil behavior. As geotechnical engineering challenges become more sophisticated, constitutive models will continue to play a crucial role in ensuring the safety and sustainability of infrastructure projects. Chapter 4. Advanced Soil Mechanics and Constitutive Models. For 2 elastoplastic models for soils. In soil mechanics, elastoplastic models are used to describe the behavior of soils that exhibit both elastic and plastic deformation under loading. These models are essential for understanding and predicting the response of soils in real-world engineering applications, where the soil undergoes reversible, elastic deformation up to a certain stress level, beyond which permanent plastic deformation occurs. Elastoplastic models are particularly useful in the analysis of soil behavior under large deformations, nonlinear stress-strain conditions, and complex loading scenarios, such as foundation, settlement, slope stability, and soil structure interaction. This section delves into the core principles of elastoplastic models, their formulation, and their application in geotechnical engineering. For point 2.1 Basic Principles of Elastoplasticity. Elastoplasticity combines elastic and plastic behaviors into a single framework. The elastic behavior is characterized by reversible deformations, where the material returns to its original shape when the applied stress is removed. Plastic deformation, on the other hand, is permanent and does not reverse once the material has yielded. In elastoplastic models, the soil undergoes elastic deformation up to a certain yield point, beyond which plastic deformation occurs. The basic principles of elastoplasticity are: elastic deformation. In the elastic range, the stress and strain are proportional and follow Hooke's law. This relationship is governed by the Young's modulus E and Poisson's ratio nu. Plastic deformation. When the applied stress exceeds a threshold, the yield point, the soil exhibits plastic deformation. Plastic flow depends on factors such as the soil shear strength and yield criteria. Yield surface. The transition between elastic and plastic behavior is described by a yield surface in stress space. When the stress state lies within the yield surface, the material behaves elastically. Once the stress state exceeds the yield surface, the soil enters the plastic regime. For point 2.2 Yield criteria for elastoplastic models. To define when soil transitions from elastic to plastic behavior, a yield criterion is used. This criterion defines the conditions under which plastic deformation starts. Some commonly used yield criteria for elastoplastic models of soils include Mohr-Coulomb criterion. This is one of the most widely used yield criteria for soils, particularly for cohesionless and cohesive soils. The Mohr-Coulomb criterion states that plastic flow occurs when the shear stress tau exceeds a critical value defined by the soil's cohesion C and the angle of internal friction phi. Tau equals C plus tan phi backslash tau equals C plus backslash sigma underscore n backslash tan backslash phi, where sigma and backslash sigma underscore n is the normal stress. The Mohr-Coulomb criterion is commonly used in both simple and advanced elastoplastic models due to its simplicity and applicability to a wide range of soils. Drucker-Prager criterion. The Drucker-Prager criterion is a smooth, continuous approximation of the Mohr-Coulomb yield surface and is often used in elastoplastic models for soils under triaxial compression. It is mathematically defined as F sigma equals sigma m plus alpha sigma d equals 0 F backslash sigma equals backslash sigma underscore m plus backslash alpha backslash sigma underscore d equals 0, where sigma m backslash sigma underscore m is the mean stress, sigma d backslash sigma underscore d is the deviatoric stress, and alpha backslash alpha is a material constant. This criterion is especially useful in numerical modeling because it simplifies the Mohr-Coulomb surface to avoid difficulties associated with the more Coulomb's non-smooth transitions. CAM clay criterion. The CAM clay model is used for clays and is based on a yield surface that expands and contracts as the soil experiences compression. This model incorporates the concept of overconsolidation and is widely used in soil mechanics to simulate the behavior of normally consolidated and overconsolidated clays. The yield surface in the CAM clay model is represented as P equals QF E, P equals Q backslash dot FE, where PP is the effective mean stress, QQ is the deviatoric stress, and E is the void ratio. This model is especially effective for predicting the consolidation behavior of clays under varying stress conditions. For 0.2.3 flow rule in elastoplastic models. In elastoplasticity, the flow rule governs how the plastic strain evolves once the soil has reached the yield surface. It defines the direction of plastic flow and the magnitude of plastic strain. The flow rule is typically associated with the yield criterion and is formulated using the associated flow rule or non-associated flow rule. Associated flow rule. In the associated flow rule, the plastic strain increments are proportional to the gradient of the yield surface. This means that the direction of plastic flow is always normal to the yield surface. It is commonly used for materials like dense sands or steep clays, where the plastic strain direction is closely aligned with the yield surface. Non-associated flow rule. In the non-associated flow rule, the direction of plastic strain does not necessarily coincide with the normal to the yield surface. This is often used in soils with more complex behavior, such as loose sands or soils with more pronounced dilatancy X. The flow rule in this case is defined by a plastic potential function, which may be different from the yield function. For 0.2.4 hardening and softening in elastoplastic models, soils exhibit both hardening and softening behavior under stress. Hardening refers to the increase in strength and steepness of the soil as it undergoes plastic deformation, while softening refers to the decrease in strength and steepness after peak stress has been reached. These behaviors can be incorporated into elastoplastic models using a hardening rule or softening rule. Isotropic hardening. In this case, the yield surface expands uniformly as the soil is compressed. This behavior is often observed in clays and cohesive soils where the soil strength increases with compaction and consolidation. An example of isotropic hardening is the CAM clay model. Kinematic hardening. In this case, the yield surface shifts in stress space as the soil undergoes plastic deformation. This is often used to model the behavior of soils under cyclic loading or stress reversal, where the soil strength does not increase uniformly, but rather is dependent on the loading history. Softening. After reaching the peak strength, some soils exhibit a reduction in strength, known as softening. This behavior can be modeled by reducing the size of the yield surface or by introducing a post-peak stress strain curve. For 0.2.5 strain hardening models, the behavior of many soils under sustained or repeated loading shows an increase in steepness with strain. This phenomenon is called strain hardening, and it is modeled in advanced elastoplastic models through the introduction of strain-dependent material parameters. Some common strain hardening models include hardening soil model. This model accounts for both elastic and plastic strain hardening. It is used to model the behavior of soils under monotonic and cyclic loading and has been widely applied to both granular and cohesive soils. The model introduces parameters such as the initial steepness and the steepness degradation to simulate the hardening process. Modified Camclay model. An extension of the Camclay model, the modified Camclay model is used to model the soil behavior under large strain loading. It incorporates both hardening and softening behavior, making it useful for describing the stress-strain response of soils in foundations and earthworks. For 0.2.6 applications of elastoplastic models in geotechnical engineering. Elastoplastic models are invaluable tools for predicting soil behavior in complex geotechnical problems. Some key applications include foundation design. Elastoplastic models help in evaluating the settlement and bearing capacity of foundations, particularly when dealing with complex loading conditions such as eccentric loading or shallow foundations in soft soils. Slope stability. Elastoplastic models are widely used to assess the stability of slopes, embankments, and excavations, especially when the soil undergoes plastic deformation due to shear failure or sliding. Earthquake engineering. Under seismic loading, elastoplastic models can simulate soil behavior under dynamic and cyclic loads, helping assess the risk of liquefaction, cyclic mobility, and soil failure during earthquakes. Soil structure interaction. Elastoplastic models are also used in the analysis of soil structure interaction, SSI, where the interaction between the structure and the underlying soil is critical for ensuring the stability and performance of the entire system. For 0.2.7 summary, elastoplastic models play a critical role in advanced soil mechanics by capturing the nonlinear and inelastic behavior of soils under complex loading conditions. By combining elasticity and plasticity into a single framework, these models provide a more accurate representation of soil response under real-world conditions. Through the use of yield criteria, flow rules, hardening/softening behaviors, and advanced material parameters, elastoplastic models are essential tools in geotechnical engineering for designing safe, resilient, and efficient infrastructure. Chapter 4: Advanced Soil Mechanics and Constitutive Models. For Point 3: Numerical Methods in Geotechnical Analysis. In Advanced Geotechnical Engineering, numerical methods are essential tools used to analyze complex soil structure systems that cannot be easily solved through analytical methods. These methods allow engineers to simulate the behavior of soil and structures under various loading conditions, predict the response of the soil-structure interaction, and assess stability, deformation, and failure. Numerical methods are particularly useful for solving nonlinear, time-dependent, and large deformation problems that occur frequently in geotechnical engineering projects. This section introduces the key numerical methods employed in geotechnical analysis, including the finite element method, FEM, finite difference method, FDM, and other computational techniques, as well as their applications in the modeling of soil behavior and soil structure interaction. For Point 3.1 Overview of Numerical Methods. Numerical methods are computational techniques that use mathematical models to approximate the behavior of complex systems. These methods discretize the problem domain, such as the soil structure system, into smaller, manageable parts, such as elements or nodes, and then solve the resulting system of equations iteratively. The two most commonly used numerical methods in geotechnical analysis are finite element method. Then this method divides the problem domain into a mesh of small, simple shapes, finite elements, such as triangles or quadrilaterals, in 2D, or tetrahedrons or hexahedrons in 3D. Each element is characterized by a set of governing equations that describe its mechanical behavior under load, and the overall solution is obtained by solving the system of equations for all elements. Finite difference method, FDM. This method is based on approximating derivatives in differential equations using finite differences. It divides the problem domain into a grid and solves the governing equations at discrete points, nodes. It is often used for problems involving flow, heat transfer, and transit analysis, such as in pore pressure distribution and consolidation problems. For Point 3.2 Finite Element Method, FEM, in geotechnical analysis. The finite element method, FEM, is widely regarded as the most powerful numerical technique for solving complex geotechnical problems. FEM is capable of handling nonlinear, time-dependent, and large deformation problems, making it ideal for simulating soil structure interaction, foundation behavior, slope stability, and tunneling. Key concepts of FEM in geotechnical engineering. Discretization. The continuous domain, such as a soil mass or structure, is discretized into small, simple shapes, finite elements. Each element is connected to adjacent elements and nodes. This mesh representation approximates the geometry and properties of the domain. Element types. Various types of elements are used in FEM, including O1D elements, used for one-dimensional problems, such as pile analysis. O2D elements. Triangular or quadrilateral elements are commonly used for plane strain or plane stress problems. O3D elements. Tetrahedral or hexahedral elements are used for three-dimensional problems. Material models. The behavior of each element is defined by its material properties, which can be linear elastic, elastoplastic, or more advanced models like viscoelastic or hyperelastic for soils. The soil structure interaction can also be modeled by incorporating interfaces and contact elements. Boundary conditions. Appropriate boundary conditions are essential for defining how the soil mass behaves at its boundaries. These could include displacement, constraints, traction forces, and infinite boundaries, such as for unbounded soil masses. Solution techniques. FEM typically employs iterative solvers, such as the direct method, conjugate gradient method, or multigrid methods to solve the system of equations. These solvers handle the large sets of linear or nonlinear equations that arise from discretizing the system. Applications of FEM in geotechnical engineering. Soil structure interaction. FEM can model the interaction between a foundation and the surrounding soil, accounting for the deformation of both the soil and the structure. This is critical in designing foundations for buildings, bridges, or offshore platforms. Settlement analysis. FEM is used to predict the settlement of foundations due to applied loads, taking into account the nonlinear behavior of soil, such as soil consolidation and plastic deformations. Slope stability. FEM can analyze the stability of slopes, embankments, and earth dams, where nonlinear material behavior and large displacements are common. The method allows for modeling of failure mechanisms such as sliding and shear failure. Tunneling and excavation. FEM is widely used to model the behavior of soils and rock masses around tunnels or excavation sites. It simulates the effects of excavation on surrounding soil, including the development of plastic zones and deformation patterns. Liquefaction analysis. FEM can be used to simulate the potential for liquefaction in loose saturated sands during seismic events, accounting for changes in pore pressure and stress redistribution. For 0.3.3 finite difference method, FDM, in geotechnical analysis. The finite difference method, FDM, is another widely used numerical technique, especially for problems involving transient conditions, such as consolidation and seepage. Analysis. Unlike FEM, which discretizes the domain into elements, FDM discretizes the domain into a regular grid and approximates the differential equations using finite differences. Key concepts of FDM in geotechnical engineering. Grid discretization. The soil domain is divided into a regular grid of nodes, where each node represents a specific point in the soil mass. The properties of the soil at each node are evaluated, and the governing equations, such as the flow equation or equilibrium equation, are solved at these nodes. Time integration for transient problems, such as consolidation or seepage, FDM, can incorporate a time-stepping approach to simulate the evolution of the system. Over time, each time step corresponds to an update in the state of the system, and the solution progresses incrementally. D'Arrent's equations. The governing differential equations are approximated using finite D'Arrent's. For example, the Laplace equation in steady-state seepage is approximated using finite D'Arrent's between neighboring nodes. Applications of FDM in geotechnical engineering. Consolidation analysis. FDM is frequently used to model the time-dependent settlement of soils due to applied loads. The method simulates how pore water pressure dissipates over time in saturated soils and the resulting deformation, seepage and flow in porous media. FDM is particularly useful for modeling seepage through soils, such as groundwater flow or permeability tests. The method is also used for predicting the flow of water through dams, levees, and foundations. Heat and mass transfer. FDM can model the transfer of heat and moisture in soils, which is critical for understanding temperature-induced deformation and the movement of chemicals or pollutants in the soil mass. For 3.4 other numerical methods in geotechnical engineering. In addition to FEM and FDM, there are other numerical techniques that have found applications in geotechnical analysis. Boundary element method, BEM. This method is particularly useful for problems involving infinite or semi-infinite domains, such as the analysis of deep foundations or soil structure interaction in large systems. BEM reduces the dimensionality of the problem by 1, making it efficient for certain applications. Discrete element method, DMDM, is used to model granular materials, such as sands and gravels, by treating them as a collection of discrete particles that interact with each other. This method is highly effective for simulating particle flow, dilatancy, and granular soil behavior under large deformations. Material point method, MPM. MPM is a hybrid method combining the strengths of both FEM and Lagrangian methods. It is used for large deformation problems such as soil failure or landslide modeling, where large movements of the soil mass are expected. For 3.5 challenges in numerical modeling. Despite the power of numerical methods, there are several challenges in applying these techniques to geotechnical engineering. Modeling complex soil behavior. Soil behavior is often highly nonlinear, time dependent, and influenced by factors such as pore pressure, plasticity, and failure mechanisms. Accurately capturing these behaviors requires sophisticated, constitutive models and careful calibration of material parameters. Mesh generation. The accuracy of numerical models depends on the quality of the mesh or grid used to discretize the problem. A poor mesh can lead to numerical errors and inaccurate results, especially for problems with complex geometries or material properties. Computational cost. Numerical methods often require significant computational resources, particularly for large-scale problems with fine meshes or time-dependent analyses. High-performance computing and parallel processing are frequently needed for these analyses. Validation and calibration. Numerical models must be carefully validated using experimental data or field observations to ensure their accuracy. The calibration of material models is crucial for obtaining reliable predictions of soil behavior. For 3.6 summary, numerical methods, particularly the finite element method, FEM, and finite difference method, FDM, are powerful tools in advanced geotechnical engineering. They enable the simulation of complex soil structure interactions, nonlinear soil behavior, and large deformations, which are common in many geotechnical problems. These methods are used extensively in foundation design, slope stability analysis, tunneling, and consolidation analysis, among other applications. While these methods are invaluable for predicting soil behavior and ensuring safe and efficient design, they also come with challenges related to model complexity, computational cost, and calibration. Nonetheless, numerical methods remain essential for advancing the field of geotechnical engineering and addressing increasingly complex engineering challenges. Chapter 4: Advanced Soil Mechanics and Constitutive Models. 4.4 Soil Consolidation and Crete Behavior. In geotechnical engineering, understanding soil consolidation and crete behavior is crucial for the analysis of long-term settlement and deformation of soils under load. These processes are driven by both pore water pressure dissipation and soil structure changes under sustained loading, making them significant for the design of foundations, embankments, dams, and other infrastructure. This section will cover the fundamental concepts of soil consolidation and crete behavior, their governing mechanisms, and the modeling approaches used to predict these phenomena in practical engineering applications. For 4.1 Overview of soil consolidation. Soil consolidation refers to the process by which soil undergoes a reduction in volume over time due to the expulsion of pore water, typically under sustained loading. This is a time-dependent process primarily governed by the consolidation theory developed by Terzaghi and Barron in the early 20th century. Consolidation is especially significant for cohesive soils such as clays, where water cannot easily escape, leading to slow but significant settlement over time. Key concepts of soil consolidation. Primary consolidation. This is the initial phase of consolidation where the majority of settlement occurs due to the expulsion of pore water. The rate of consolidation is governed by the coefficient of consolidation, CV, which depends on the permeability of the soil, the thickness of the soil layer, and the compressibility of the soil. Secondary consolidation. Creep after primary consolidation is complete. Some soils continue to undergo additional settlement due to changes in the soil structure, even after the pore water pressure has dissipated. This is referred to as secondary consolidation or creep and occurs at a much slower rate. Void ratio and ejective stress. During consolidation, the void ratio, the ratio of the volume of voids to the volume of solids, decreases as the pore water is expelled, and the ejective stress in the soil increases. The relationship between ejective stress, void ratio, and consolidation can be described using the consolidation equation. Governing equations for consolidation. The one-dimensional consolidation process is typically described by the Terzaghi's consolidation equation, which relates the time rate of settlement to the soil's permeability, compressibility, and drainage conditions. Del 2U del T2 equals CV del 2U del Z2 \frac partial caret 2U partial T squared equals C underscore V dot frac partial caret 2U partial Z squared, where UU is the pore water pressure, TT is time, ZZ is the vertical coordinate, CDC underscore V is the coefficient of consolidation. This equation is solved under boundary conditions for practical applications, and it can be used to predict the settlement of soils under long-term loading conditions. Consolidation testing. Oedometer test. The standard laboratory test for measuring the consolidation properties of soils is the oedometer test, also known as the consolidation test. During this test, a soil sample is subjected to a series of incremental vertical loads, while the vertical displacement, settlement, and pore water pressure are monitored. The data from this test are used to determine the coefficient of consolidation, CV, the compression index, CC, and the rebound index, CR, which are essential for predicting the consolidation behavior of the soil. Field consolidation tests. In situ tests, such as the CPT, cone penetration test, or piezo test, can also be used to estimate consolidation properties indirectly by measuring the pore water pressure response and soil steadiness. For 0.4.2 creep behavior in soils. Creep in soils refers to the gradual, time-dependent deformation under constant applied stress occurring after the completion of primary consolidation. Unlike consolidation, where the soil volume decreases mainly due to the expulsion of pore water, creep is due to the rearrangement of soil particles, and the change in soil structure over time. Key concepts of creep behavior. Secondary compression. Creep once primary consolidation has been completed. Secondary compression occurs due to the time-dependent rearrangement of soil particles, particularly in fine-grained soils like clays. This deformation continues even after pore pressure dissipation is complete and can last for many years or decades. Rate of creep. The rate of creep is typically slow and decreases over time. The rate is highly dependent on the over-consolidation ratio, the clay mineralogy, and the initial state of stress in the soil. Creep is more pronounced in soft clays and organic soils. Factors affecting creep. Active stress. The greater the active stress on the soil, the more likely it is to exhibit creep behavior. Water content. Higher water content in the soil may reduce particle interaction, making the soil more susceptible to creep. Soil structure. Clays with a more compact or over-consolidated structure exhibit less creep than those in a normally consolidated state. Mathematical modeling of creep. Creep behavior is often modeled by empirical relationships or theoretical models that describe the time-dependent strain after consolidation. A commonly used model to describe secondary consolidation is the logarithmic model, which assumes that the strain increases logarithmically with time after primary consolidation. S equals clog T backslash epsilon underscore S equals C underscore backslash alpha backslash log T, where S backslash epsilon underscore S is the secondary strain creep. C alpha C underscore backslash alpha is the creep index, a material constant. Tt is time. This equation suggests that the rate of creep decreases over time, with the strain becoming asymptotic as time progresses. Creep testing. Oedometer creep test. The creep component of the consolidation process can be evaluated in an oedometer test by applying a constant load after the completion of primary consolidation. The subsequent vertical strain settlement is monitored over time to assess the rate of secondary consolidation or creep. Field observations. Long-term settlement data from field measurements, such as those obtained from settlement plates or extensometers, are often used to estimate the creep behavior of soils in real-world applications. This is particularly important in projects like embankments, levees, and deep foundations where secondary settlement due to creep can be a concern. For 4.3 consolidation and creep in geotechnical engineering applications. Foundation design. The prediction of settlement due to consolidation is crucial for the design of foundations, particularly for structures that are sensitive to long-term deformation, such as tall buildings, bridges, and storage tanks. Secondary Consolidation or creep must also be considered to ensure that excessive long-term settlement does not occur. Embankment and dams. In the design of embankments and dams, consolidation and creep behavior play an important role in predicting the long-term settlement of the structure and the underlying soil. Pore pressure generated during construction and the long-term reduction of pore pressure are key factors in determining stability. Land reclamation. In land reclamation projects, where soils are often deposited over soft, compressible marine sediments, the consolidation process can take several years or even decades. Engineers must account for both primary and secondary consolidation to assess long-term settlement and infrastructure integrity. Tunnels and underground structures. In tunneling, consolidation and creep behavior of surrounding soils must be considered to predict ground movement and settlement around tunnel shafts. Soil creep, in particular, can a ECT tunnel lining design and long-term performance. For 4.4 Advanced Modeling of Consolidation and Creep. Numerical methods, particularly the finite element method, FEM, have become indispensable for modeling complex consolidation and creep behavior in soil structure systems. Advanced numerical models can simulate multi-phase flow, pore pressure, and water content interaction, nonlinear consolidation behavior, especially for overconsolidated clays, time-dependent creep deformation over long time periods. More sophisticated models, such as the modified CamClay model, can incorporate both primary and secondary consolidation in a unified framework, capturing both the stress, strain behavior of soils and their long-term settlement behavior. For 4.5 summary, soil consolidation and creep behavior are crucial considerations in the design and analysis of many geotechnical structures. Consolidation describes the time-dependent settlement of soils due to the expulsion of pore water under load, while creep refers to the long-term deformation of soils due to rearrangement of soil particles after primary consolidation. Both phenomena must be carefully modeled to predict long-term settlements, stability, and overall performance of geotechnical systems. Numerical techniques, such as FEM, have become essential in modeling these complex behaviors, providing engineers with the tools to design more accurate and efficient systems for a wide range of geotechnical applications. Chapter 4: Advanced Soil Mechanics and Constitutive Models. 4.5 Soil liquefaction and its modeling. Soil liquefaction is a phenomenon in which saturated, unconsolidated soils lose their strength and steadiness during and after an earthquake or other rapid loading events. The sudden loss of strength in loose, saturated sands can cause the soil to behave more like a liquid than a solid, leading to catastrophic ground settlement, lateral spreading, and damage to structures. Liquefaction is one of the most critical issues in earthquake engineering, and understanding its mechanisms, behavior, and modeling is essential for the safety and stability of infrastructure in seismically active areas. This section discusses the mechanisms of soil liquefaction, factors influencing its occurrence, and the advanced modeling techniques used to predict liquefaction behavior during seismic events. For 5.1 Mechanisms of soil liquefaction. Liquefaction occurs when the pore water pressure within a saturated soil increases to the point where it reduces the ejective stress between the soil particles, causing them to lose their ability to resist shear stresses. This phenomenon primarily occurs in loose, saturated sands and is triggered by dynamic loading such as an earthquake or rapid loading. Key mechanisms of liquefaction. 1. Shear stress is induced by seismic shaking. During an earthquake, the shaking causes shear stresses within the soil. These stresses generate pore water pressures, particularly in loose granular soils, which causes a reduction in the ejective stress that holds the soil particles together. When the pore pressure equals or exceeds the ejective stress, the soil behaves as a fluid, losing its shear strength. 2. Increase in pore water pressure. The sudden application of dynamic loading leads to an increase in pore water pressure, particularly in sands with low permeability. As the pore water pressure increases, the interparticle friction between the sand grains decreases, leading to the loss of shear strength. 3. Reduction in ejective stress. Ejective stress is the difference between the total stress applied to the soil and the pore water pressure. In a liquefied state, the ejective stress becomes very small or even zero, leading to the soil's inability to support vertical or horizontal loads. This results in the soil flowing and failing under minimal stress. Conditions for liquefaction. Liquefaction generally occurs under the following conditions. Loose, saturated sands. Liquefaction is most likely to occur in loose, granular soils that are fully saturated with water. Dynamic loading. Earthquake shaking or rapid load application is typically required to trigger liquefaction. Low overburden stress. Shallow soils with lower overburden pressure are more susceptible to liquefaction because the pore pressure can more easily exceed the ejective stress in these conditions. For 5.2 Consequences and EX of liquefaction. The consequences of soil liquefaction can be severe, leading to significant damage to infrastructure and loss of ground stability. Common EX include lateral spreading. Liquefied soils may lose strength and deform laterally, leading to ground displacement and damage to structures like roads, bridges, and pipelines. Ground settlement. After liquefaction, the ground may settle as the soil loses its ability to support loads. This is particularly problematic in areas with structures or infrastructure built on the soil. Tilt and collapse of structures. buildings, tanks, and other structures may tilt or collapse due to the loss of foundation support, as the underlying soil behaves like a liquid and cannot provide the necessary bearing capacity. Sand boils. The upward migration of pore water through the soil can result in the formation of sand boils, also known as liquefaction-induced sand eruptions, at the surface. These features are caused by the release of water under high pressure during liquefaction, leading to surface disruption. For 0.5.3 factors affecting liquefaction susceptibility. Several factors influence the susceptibility of soil to liquefaction, including the following: soil type and density. Loose, clean sands and silts are most prone to liquefaction. Well-graded and dense soils are less susceptible to liquefaction because they have greater internal friction and resistance to pore pressure buildup. Depth to water table. Liquefaction typically occurs in saturated soils, so the depth of the water table is an important factor. Soils located above the water table are less likely to experience liquefaction. Overburden pressure. Higher overburden pressures reduce the potential for liquefaction by increasing the active stress. Shallow soils are more prone to liquefaction compared to deeper soils. Magnitude and duration of seismic shaking. Stronger earthquakes with longer durations are more likely to induce liquefaction. The cyclic shear strain generated during shaking is a critical factor in determining whether liquefaction will occur. Soil permeability. Soils with low permeability, such as siltous sands and clays, allow pore pressure to build up more easily and prevent rapid drainage, making them more susceptible to liquefaction. For 0.5.4 liquefaction modeling approaches. Advanced geotechnical models are used to assess the potential for liquefaction and predict its behavior during an earthquake. These models typically integrate site-specific soil data, dynamic loading conditions, and pore pressure buildup during shaking. The two main approaches for modeling liquefaction are: 1. Simplified liquefaction models. Simplified models use empirical relationships based on laboratory and field data to predict the likelihood of liquefaction at a specific site. These models provide rapid and practical solutions for evaluating liquefaction potential, but are often limited in their ability to account for more complex behaviors. Seed and Idris method, 1971. One of the most widely used simplified methods for liquefaction evaluation. This method uses the cyclic resistance ratio, CRR, and cyclic stress ratio, CSR, to assess the likelihood of liquefaction. The CSR represents the induced shear stress from an earthquake, while the CRR represents the soil's resistance to liquefaction. Liquefaction resistance. The CRR is typically determined from cone penetration test, CPT data, standard penetration test, SPT, results, or laboratory tests. The CSR is calculated based on earthquake magnitude, depth, and ground acceleration. 2. Advanced numerical models for liquefaction. More advanced models are used to simulate the behavior of soils under dynamic loading, conditions, and pore pressure development. These models typically involve finite element analysis, FEM, or finite difference methods, FDM, to simulate the cyclic behavior of soils and the development of pore pressure during seismic events. Active stress and undrained models. In these models, the soil behavior is represented by an undrained cyclic loading model that accounts for the buildup of pore water pressure and the resulting reduction in active stress. Plasticity-based models, such as the modified Kamklay model, can be used to simulate the non-linear behavior of soil under cyclic loading. Multiphase flow and liquefaction models. Some models incorporate multiphase flow and soil-water interaction during dynamic loading. These models simulate the interaction between solid particles and pore water, allowing for more realistic predictions of liquefaction behavior. Cyclic mobility and densification models. These models predict the cyclic mobility of the soil as well as its densification or contraction during repeated loading. The cyclic mobility is a measure of the soil's ability to deform under dynamic loads, while densification can reduce liquefaction potential by increasing soil density. 3. Post-liquefaction models. Once liquefaction has occurred, it is important to model the post-liquefaction behavior of the soil. Dissipation of pore pressure and consolidation can ECT the soil's stability and its ability to regain strength. Numerical models typically simulate the recovery of active stress over time and the post-liquefaction settlement. 4.5.5 Mitigation strategies for liquefaction. Several methods are used to mitigate the effects of liquefaction and reduce the risk of damage during an earthquake. Ground improvement. Techniques such as vibrocompaction, dynamic compaction, or soil grouting can be used to densify the soil and reduce its susceptibility to liquefaction. Drainage systems. Installing drainage systems, such as wick drains or sand drains, can help accelerate pore pressure dissipation and reduce the likelihood of liquefaction during seismic events. Deep foundations. For structures built on liquefiable soils, deep foundations such as piles or caissons can provide a stable base by extending below the liquefiable layers. Seismic isolation. Base isolators or other forms of seismic protection can be used to minimize the impact of ground shaking on structures, reducing the potential for damage due to liquefaction-induced settlement. 4.5.6 Summary. Soil liquefaction is a complex and dangerous phenomenon that occurs when saturated, loose soils lose their strength and behave like a liquid under seismic loading. The Susceptibility to liquefaction depends on factors such as soil type, density, water table, depth, and the magnitude of earthquake shaking. Advanced modeling techniques, including simplified empirical methods and sophisticated numerical simulations, are essential tools for assessing liquefaction potential and predicting the behavior of soils during seismic events. By understanding and modeling liquefaction, engineers can design more resilient structures and implement effective mitigation strategies to reduce the impact of this phenomenon. Chapter 4: Advanced Soil Mechanics and Constitutive Models. For point 6, recent advances in constitutive modeling. Constitutive models are essential tools in geotechnical engineering as they describe the relationship between the stress and strain in soils under various loading conditions. Advances in constitutive modeling have led to more accurate predictions of soil behavior, enabling better design and risk management for geotechnical structures. This section highlights the latest developments in constitutive models for soils, including improvements in material behavior descriptions, computational techniques, and the integration of advanced experimental data. For point 6.1, evolution of constitutive models in geotechnical engineering. Traditional constitutive models, such as the Mohr-Coulomb model and the linear elastic model, have been widely used in geotechnical applications. However, these models have limitations in capturing the complex, nonlinear, and time-dependent behavior of soils under various loading conditions. As research in soil mechanics advances, newer models have been developed that can better represent the inherent complexities of soil behavior, especially under cyclic, non-drained, or dynamic loading. The key areas of recent developments include nonlinear models, addressing the nonlinear relationship between stress and strain, especially for large deformations and high-stress states. Time-dependent models, capturing time-dependent soil behavior including consolidation and creep. Soil structure and fabric modeling, introducing more sophisticated representations of the internal structure of soils and their ECT on soil behavior. For point 6.2, advanced soil models, key developments. 1. Elastoplastic models with nonlinear hardening. Recent advancements in elastoplastic models include enhanced descriptions of soil yield, surfaces, hardening behavior, and the introduction of more refined models to better capture soil behavior under different loading conditions. Modified Kamklay model. The modified Kamklay model, a widely used elastoplastic model, has been extended to account for more complex behaviors, such as anisotropic hardening and stress history (EX). This model describes both the yield surface and the plastic flow rule, providing insights into the material's response under varying stress conditions, particularly in over-consolidated soils. Bounding surface plasticity models. This class of models introduces bounding surfaces to represent stress states in soils under both elastic and plastic deformation. They capture the transition between elastic and plastic zones more realistically and are particularly useful for simulating large strain behaviors during cyclic loading and soil loading-unloading cycles. These models have applications in deep foundations and embankment construction. 2. Hypoplastic models. Hypoplasticity has emerged as an alternative to the conventional elastoplastic theory for modeling soil behavior. Unlike elastoplastic models that assume a well-defined yield surface, hypoplastic models do not require a yield surface and can capture the entire stress-strain behavior of soils over a wider range of stress states. They are particularly beneficial for modeling highly nonlinear soil responses. Advancements in hypoplastic models. Recent hypoplastic models incorporate stress history, shear dilatancy, and time-dependent EX like creep. These models also improve the description of soil hardening and softening under various loading conditions. 3. Soft soil models. Soft soils, such as clays, exhibit complex behaviors under loading due to their high compressibility and time-dependent characteristics. Recent developments in soft soil models have focused on enhanced consolidation modeling, incorporating viscoelastic and viscoplastic elements to better describe the time-dependent behavior of soft soils during consolidation and post-consolidation. Anisotropic consolidation, recognizing the directional properties of soft clays, e.g., dearences in behavior between vertical and horizontal directions more. Advanced models now consider anisotropic consolidation, which is crucial for better understanding soil behavior in deep foundations, embankments, and coastal works. 4. Cyclic and dynamic loading models. Soils subjected to cyclic loading, such as those experienced during earthquakes, exhibit a nonlinear, hysteretic response that is challenging to model accurately. Advances have focused on improving models that can capture soil response under cyclic and dynamic loading conditions. Modified Mazing Model. The modified mazing model extends traditional mazing type models by improving the representation of cyclic loading with a focus on hysteresis and strain accumulation during repeated loading cycles. This model is frequently applied to assess the behavior of granular soils under cyclic loading, e.g., in liquefaction studies. Viscoelastic viscoplastic models for cyclic loading. Newer models, such as viscoelastic viscoplastic models, have been developed to describe the rate dependent behavior of soils subjected to cyclic loads. These models are crucial for predicting earthquake-induced settlements, liquefaction potential, and dynamic soil structure interaction. 5. Multiphase flow models and saturation EX. Recent advances have also included multiphase flow models that account for the interaction between solid particles, pore water, and gases in the soil. These models are essential for predicting behaviors such as liquefaction and pore pressure development during dynamic loading events. Multiphase porous media models. These models represent soils as a mixture of water, air, and solid phases and consider the interaction between these phases. They can be used to simulate processes such as dissipation of pore water, pressure and consolidation in both saturated and partially saturated soils. Unsaturated soil models. Advances in unsaturated soil mechanics have led to the development of constitutive models that accurately describe the behavior of soils with varying levels of saturation, such as those found in drought-prone regions or shallow foundations. These models use the suction stress concept and incorporate the capillary pressure and saturation degree. For 0.6.3 integration of advanced experimental data. A key factor in the development of advanced constitutive models is the integration of experimental data obtained from cutting-edge laboratory testing and field monitoring techniques. Some of these include triaxial tests, the introduction of advanced triaxial testing techniques, such as the cyclic triaxial test, has led to a deeper understanding of cyclic soil behavior, including the identification of residual strength, dilatancy, and ratcheting EX in soils. Laboratory imaging techniques. Advances in microscopic imaging, such as X-ray, tomography, and electron microscopy, have allowed for the observation of soil microstructure changes during loading. These techniques are essential for understanding the fabric evolution in soils and the development of more accurate soil models that reflect internal structure changes. Field monitoring. The use of advanced geophysical methods, such as seismic, wave propagation, and dynamic probing, allows engineers to better understand in situ soil properties and calibrate constitutive models to actual field conditions. For 0.6.4 computational advancements and modeling approaches. Recent advances in computational geotechnics have made it possible to apply more sophisticated constitutive models to large-scale engineering problems. This includes finite element analysis, FEA, the incorporation of advanced constitutive models into finite element analysis, FEA, software has become more widespread, allowing for the simulation of complex soil structure interactions and nonlinear behavior under both static and dynamic loading. Parallel computing and high-performance computing, HPC. With the increase in computational power, it is now possible to solve more complex geotechnical models in less time, making it feasible to model large, real-world engineering problems with higher accuracy. Coupled analysis. Advanced models now allow for coupled analyses between soil mechanics and fluid dynamics, for example, in the study of pore pressure, dissipation during dynamic loading and coupled consolidation processes. For 6.5 future directions in constitutive modeling. As research in soil mechanics continues to advance, several future directions are likely to influence constitutive modeling in geotechnical engineering, machine learning and AI. The application of machine learning and artificial intelligence in soil modeling is an exciting development. By leveraging large datasets, these techniques could optimize the calibration of constitutive models and assist in predicting soil behavior under complex loading conditions. Multiscale modeling. Future developments in multiscale modeling aim to connect micro-level, particle-level behavior with macro-level soil responses. This could improve the accuracy of models, particularly in complex soils like cohesive, frictional mixtures. Integrated site characterization, combining advanced constitutive models with real-time monitoring of soil properties, e.g., using remote sensing or Internet of Things (IoT) devices, could lead to better informed decisions for infrastructure design and management. For 6.6 summary, recent advances in constitutive modeling have led to a more comprehensive understanding of soil behavior under various loading conditions. By incorporating nonlinear behavior, time-dependent EX, dynamic loading, and the microstructural changes of soils, modern models provide more accurate predictions of soil performance. These advances, combined with sophisticated computational techniques and experimental data, have enhanced the ability to design safer and more efficient geotechnical structures. As computational power continues to increase and new research emerges, constitutive models will continue to evolve, improving our ability to address complex geotechnical challenges. Chapter 5: Foundation Engineering. 5.1 Shallow Foundations. Design and Analysis. Shallow foundations are the most commonly used foundation type in geotechnical engineering, designed to transfer the loads from structures to the underlying soil at a relatively shallow depth. These foundations are typically used when the bearing capacity of the soil near the surface is adequate to support the structure, making them cost-effective and easy to construct. In this section, we will explore the principles, design methods, and analysis of shallow foundations, focusing on their behavior under various loading conditions, soil types, and environmental factors. 5.1.1 Types of Shallow Foundations. Shallow foundations are typically classified into the following types based on their structural design and the loads they carry. Spread footings. These are the most common type of shallow foundation, where a wide base is used to distribute the load over a large area of soil. Spread footings are typically used for low to medium-rise buildings and are designed for uniform or nearly uniform soil conditions. Strip footings. These are linear footings used to support walls or load-bearing elements. They are typically long, narrow foundations that are placed directly beneath continuous walls or structures. Mat foundations. Also known as raft foundations, mat foundations are large, thick slabs that cover the entire area beneath a structure. They are used when the soil bearing capacity is low or when settlements need to be minimized by distributing the load over a wide area. Slab on grade. This is a continuous concrete slab that rests on the ground surface. It is typically used in low-rise buildings where the soil beneath is firm enough to support the load without excessive settlement. Slab and beam foundations. A combination of beams and a slab that provides a level platform for the structure. The slab and beams are placed at shallow depths, supported by underlying soil. 5.1.2 Soil bearing capacity and settlement criteria. The primary goal of shallow foundation design is to ensure that the soil beneath the foundation can safely support the applied loads without excessive settlement, shear, failure, or tilting of the foundation. The design process begins with an evaluation of the soil's bearing capacity and its ability to resist deformation. 1. Ultimate bearing capacity. The ultimate bearing capacity of soil is the maximum pressure that can be applied at the foundation-soil interface without causing failure due to shear failure of the soil beneath the foundation. It can be determined using several methods, including Terzagh's bearing capacity equation. This classic formula provides an estimate of the ultimate bearing capacity for a shallow foundation. Cult equals CNC plus sigma V and sigma plus QNQQ underscore ULT equals CN underscore C plus backslash sigma underscore V N underscore backslash sigma plus QN underscore Q, where occult underscore ULT equals ultimate bearing capacity. OCC equals cohesion of the soil. ONC N sigma NQN underscore C N underscore backslash sigma N underscore Q equals bearing capacity factors, which depend on the soil's friction angle and depth. O sigma V backslash sigma underscore V equals vertical ejective stress at the foundation depth. OQQ equals depth of the foundation. Rankin's earth pressure theory. In some cases, Rankin's theory is used to estimate bearing capacity, especially when dealing with sloped or layered soils. 2. Allowable bearing capacity. The allowable bearing capacity is a reduced value of the ultimate bearing capacity, chosen to account for factors like safety margins, material variability, and potential future settlements. A factor of safety, typically between 2 and 3, is applied to ensure that the soil will not fail under the applied loads. This value is determined by call equals cult FSQ underscore all equals backslash frac Q underscore ULT FS. where FSFS is the factor of safety. 3. Settlement considerations. Excessive settlement of a foundation can lead to structural damage and operational issues. Settlement is primarily governed by soil deformation and consolidation. The following factors influence settlement. Immediate settlement. This occurs when the foundation is first loaded and the soil undergoes elastic deformation. Consolidation settlement. This is a time-dependent settlement that occurs in cohesive soils, particularly clays, due to the expulsion of pore water over time. Differential settlement. This occurs when the foundation settles unevenly due to variations in soil steepness or load distribution. To minimize settlement, it is critical to ensure that the foundation is placed at an adequate depth to avoid soft surface soils. Optimize the foundation design to distribute the load uniformly across the soil. 5.1.3 Bearing capacity factors and load factors. To accurately determine the bearing capacity of shallow foundations, various bearing capacity factors are used, which depend on the type of foundation, the soil properties, and the applied load. These factors, typically derived from experimental data or empirical research, vary for different soil types, e.g., sand, clay, gravel, and loading conditions, e.g., static, dynamic, cyclic. Common factors influencing bearing capacity are shape factor, as the foundation shape influences the bearing capacity. 4. Example: square and circular footings generally perform better than rectangular ones in terms of capacity. Depth factor: d. the depth of the foundation relative to the width of the footing. X. the bearing capacity. Increasing depth usually increases the capacity, but diminishing returns are seen after a certain point. Inclination factor: I. foundations subjected to inclined loads will experience reduced bearing capacity compared to those with vertical loads. Load inclination: the angle at which the load is applied also impacts the foundation's performance, with inclined loads reducing the bearing capacity. Soil type: cohesionless soils, e.g., sand, and cohesive soils, e.g., clay, have very different bearing characteristics and thus require different models for analysis. 5.1.4 Shallow foundation design process. The design of shallow foundations involves the following steps. 1. Site investigation and soil testing. A thorough site investigation is required to assess the subsurface conditions. This includes performing geotechnical tests such as standard penetration tests, SPT, cone penetration tests, CPT, laboratory soil tests, e.g., triaxial tests, shear tests, and geophysical surveys to determine the soil's properties, such as cohesion, friction angle, and compaction. 2. Determination of bearing capacity. Using the results from the site investigation, the bearing capacity of the soil is determined. using methods like Terzaghis. Bearing capacity equation and safety factors. 3. Settlement calculation. Settlement is estimated based on soil properties, foundation dimensions, and the applied load. The objective is to ensure that settlements do not exceed acceptable limits. This includes both total settlement and differential settlement. 4. Factor of safety. FS. The factor of safety is applied to ensure that the foundation is designed conservatively, considering uncertainties in soil properties and loading conditions. 5. Selection of foundation type and size based on the bearing capacity and settlement considerations. The appropriate foundation type, e.g., spread footing, mat foundation, and dimensions, width, depth, are selected. The foundation size is designed to distribute the load evenly to avoid failure and excessive settlement. 6. Foundation depth. The depth of the foundation is determined based on the type of soil, the imposed load, and the required bearing capacity. A deeper foundation is typically used in weak or compressible soils, while shallow foundations are sufficient for stronger soils. 7. Final design and detailing. The final design involves selecting materials for the foundation, determining reinforcement details, and ensuring that the foundation is adequately anchored and stable. 5.1.5 Load distribution and structural considerations. The distribution of load on the foundation depends on the type of foundation and the characteristics of the supporting soil. In spread footings, the load is distributed to the soil in the form of a uniform pressure distribution. In deep foundations, the load is transferred through piles or caissons to deeper, stronger soil layers. When designing the foundation structure, factors such as geotechnical shear strength, settlement tolerances, and soil structure interaction must be considered. The foundation must also be designed to resist overturning, sliding, and uplift forces, particularly in areas with high seismic activity or wind loading. 5.1.6 Challenges in shallow foundation design. Several challenges can arise in shallow foundation design. Soil heterogeneity. Variations in soil properties at the site can lead to differential settlement or failure. Detailed site characterization and in situ testing are critical to address this challenge. Liquefaction. In areas with loose, saturated soils, the risk of liquefaction during earthquakes can pose significant challenges. Liquefaction may cause foundation displacement and structural damage. Erosion and scouring. Shallow foundations in coastal or riverine environments may be affected by erosion or scouring, which can reduce the foundation's bearing capacity. Shrinkage and swelling. Expansive soils, which undergo volume changes with moisture fluctuations, can cause uneven settlement and cracking in foundations. 5.1.7 Conclusion. Shallow foundation design is a critical aspect of geotechnical engineering as it ensures that the structure is supported by stable and reliable soil. By understanding the soil's bearing capacity, calculating settlement, and considering safety factors, engineers can design shallow foundations that safely transfer loads from structures to the soil. Advances in geotechnical testing, modeling techniques, and computational tools continue to improve the accuracy of shallow foundation design, ensuring the safety and longevity of built structures. Chapter 5: Foundation Engineering. 5.2 Deep foundations, piles, and drilled shafts. Deep foundations are employed when the surface soils cannot provide sufficient bearing capacity for the loads of a structure, or when excessive settlement would occur. These foundations transfer the load to deeper, more stable soil or bedrock layers. The two most common types of deep foundations are piles and drilled shafts. This section provides an overview of these foundation types, their design, construction methods, and performance under direct loading conditions. 5.2.1 Types of deep foundations. 1. Piles. Piles are long, slender structural elements driven or placed into the ground to transfer loads to deeper soil or rock layers. They are typically made of concrete, steel, or wood, and can be classified into the following types. End-bearing piles. These piles transfer the load to a stronger layer of soil or rock beneath the pile tip. The load is primarily resisted by the soil beneath the pile tip. Friction piles. In these piles, the load is transferred through friction between the pile surface and the surrounding soil. They are typically used when the underlying soil does not provide adequate bearing capacity at the pile tip. Combination piles. These piles combine both end-bearing and frictional resistance. The load is distributed to both the pile tip and the surrounding soil along the length of the pile. Piles are used in various applications, such as in marine environments, soft soils, or seismic areas where the soil conditions are highly variable or unstable. 2. Drilled shafts. Drilled shafts, also known as bored piles or caissons, are large diameter concrete shafts drilled into the ground to transfer loads to deeper, more competent soil or rock layers. Unlike driven piles, drilled shafts are constructed by drilling a hole, which is then filled with concrete, reinforcing steel, and sometimes grout. They can be used in both cohesive and granular soils, providing significant load-bearing capacity. Drilled shafts are typically used in areas with deep layers of soft or loose soils. Locations where vibrations from pile driving must be minimized, e.g., near sensitive structures. Foundation elements for large or tall structures, bridges, or high-rise buildings. 5.2.2 Design and analysis of piles. The design of piles requires an understanding of both the geotechnical conditions of the site and the structural capacity of the pile. The primary factors that influence pile design include pile type, soil properties, pile material, and the load to be transferred. 1. Pile capacity. Pile capacity is determined by the bearing capacity of the soil at the pile tip and the skin. Friction, frictional resistance along the pile shaft. Pile capacity is generally calculated using the following methods. Static load tests. These tests are performed to determine the actual load capacity of a pile by applying a load to the pile until it reaches failure or maximum displacement. The test data can be used to predict the pile's behavior under normal loading conditions. Empirical formulas. Several empirical formulas can estimate pile capacity, such as Terzaghi and Peck's method for friction piles, or Meyerhoff's formula for end bearing piles. These formulas require input parameters such as soil cohesion, friction angle, and pile dimensions. The ultimate load capacity of a pile, Q_ULT, can be expressed as Cult equals tip plus shaft Q_ULT equals Q_tip plus Q_shaft, where O tip Q_tip is the load carried by the tip of the pile in bearing resistance. Oak shaft Q_shaft is the load carried by the friction between the pile surface and the surrounding soil. 2. Pile load transfer. The load transfer to the pile is generally analyzed using the load displacement curve, which describes how the pile settles under increasing load. The pile's performance is determined by both the tip resistance, load transferred through the pile tip and shaft, friction, load transferred along the pile's surface. Load transfer methods, such as the TZ method or the QZ method, are often employed to model this interaction. TZ method. In this method, the resistance between the pile shaft and surrounding soil is divided into discrete segments. Each segment's resistance is modeled as a function of displacement. QZ method. This method models the total load carried by the pile as a function of the displacement of the pile, considering both the shaft and tip resistances. 3. Factors affecting pile performance. Several factors influence the performance of piles. Soil type. The type of soil surrounding the pile significantly affects its capacity. 4. Example: piles in soft clay or silt will rely more on friction along the shaft, while piles in dense sands or rock will provide end-bearing resistance. Pile length and diameter. The length of the pile determines the depth at which the load is transferred, while the diameter affects the amount of surface area for frictional resistance. Pile group EX. When multiple piles are used in a group, the piles interact with each other, which can affect the total load capacity and settlement. Pile group efficiency decreases as the distance between piles decreases, especially in cohesive soils. Soil structure interaction. The interaction between the pile and surrounding soil is crucial for predicting the pile's behavior under load. This interaction is influenced by soil steepness, pile material, and pile geometry. 5.2.3 Design and analysis of drilled shafts. Drilled shafts are typically larger in diameter than piles and are often used for large-scale projects such as bridges, high-rise buildings, and heavy industrial structures. They provide excellent capacity for both axial loads and lateral loads. 1. Shaft capacity. The shaft capacity of a drilled shaft is determined by the skin friction along the shaft, while the tip capacity is determined by the end-bearing resistance at the bottom of the shaft. The total capacity of the drilled shaft is the sum of these two components. Total equals shaft plus tip Q underscore total equals Q underscore shaft plus Q underscore tip. Shaft capacity. The skin friction is evaluated based on the frictional resistance between the shaft and the surrounding soil. The friction is typically higher in dense soils and lower in soft clays. Tip capacity. The tip capacity is determined by the soil or rock strength at the bottom of the shaft. This is especially important in areas with hard rock layers. 2. Drilled shaft load transfer. Similar to piles, the load transfer in drilled shafts is governed by skin friction and tip resistance. The load transfer curve is used to assess how the load is transferred through the shaft and tip. The shaft's load transfer is influenced by soil type. Cohesive soils, like clay, owe greater skin friction, while granular soils, like sand, rely more on end-bearing capacity. Pile length and diameter. Larger diameter shafts have more surface area for friction, improving their load-bearing capacity. 3. Drilled shaft construction. The construction of drilled shafts typically involves the following steps. Drilling. A borehole is drilled into the ground to the required depth using a drill rig. The diameter of the borehole is often larger than the required shaft diameter to allow space for the insertion of reinforcement and concrete. Casing. Temporary casing may be used to prevent collapse of the borehole, especially in loose or granular soils. The casing is removed as the shaft is poured with concrete. Reinforcement. Steel reinforcement is placed within the borehole to provide the required strength for the shaft. Concrete pouring. Concrete is poured into the borehole to form the shaft. The concrete mix should be designed to achieve sufficient strength and stability. 5.2.4 Performance of deep foundations. Deep foundations are designed to provide reliable load transfer even in challenging soil conditions. Their performance is influenced by soil and rock properties. The capacity and behavior of deep foundations are highly dependent on the soil and rock conditions at the site. For example, piles and dents. Sand may perform very well under axial loads, while piles and soft clay may rely heavily on friction. Load distribution. The load distribution between piles and drilled shafts can vary, depending on the soil steepness, the type of loading, static or dynamic, and the depth of the foundation. Deep foundations often require precise modeling to ensure that loads are distributed efficiently and that settlements remain within acceptable limits. Environmental conditions. Deep foundations can be affected by environmental factors such as groundwater levels, chemical attack, or freeze-thaw cycles. Protective coatings or special materials may be required to mitigate these effects. 5.2.5 Conclusion. Deep foundations, including piles and drilled shafts, provide essential solutions for supporting structures when shallow foundations are not feasible due to weak or variable surface soils. The proper design, analysis, and construction of these foundations depend on understanding the soil and rock conditions, the structural requirements, and the load distribution. By selecting the appropriate type of deep foundation and accurately assessing its capacity, engineers can ensure safe and effective load transfer, minimizing risks of settlement and structural failure in challenging environments. Chapter 5. Foundation Engineering. 5.3 Foundation Settlement and Bearing Capacity. Foundation settlement and bearing capacity are two critical aspects in foundation design that must be carefully considered to ensure the safety and performance of any structure. The bearing capacity defines the maximum load that the soil beneath the foundation can support without failure, while settlement refers to the vertical displacement of the foundation as it carries the applied load. Both of these factors are vital in determining whether the foundation will perform adequately under expected conditions. This section will provide a detailed overview of foundation settlement, bearing capacity, and methods to assess and manage both. 5.3.1 Bearing capacity of foundations. The bearing capacity of a foundation refers to the ability of the soil beneath the foundation to support the imposed loads without undergoing failure due to shear. When designing a foundation, engineers must evaluate the soil's strength and its capacity to resist failure under different loading conditions. 1. Ultimate bearing capacity. The ultimate bearing capacity of a foundation is the maximum pressure that the soil can withstand before failure occurs, either through shear failure in the soil or tilting of the foundation. It is typically determined using theoretical methods, such as Terzaghi's equation for shallow foundations, which accounts for soil cohesion, friction angle, and depth of the foundation. The formula for calculating the ultimate bearing capacity, calc_ULT, of a foundation is Cult equals CNC plus sigma V and Q plus Q and gamma Q underscore ULT equals Cn underscore C plus backslash sigma underscore Vn underscore Q plus Qn underscore backslash gamma, where Cc equals cohesion of the soil and Kn slash M superscript 2, Nc, Nq, N gamma N underscore C, N underscore Q, N underscore backslash gamma equals bearing capacity factors that depend on the type of soil and depth. Sigma V backslash sigma underscore V equals vertical effective stress at the depth of the foundation. QQ equals depth of the foundation. 2. Allowable bearing capacity. The allowable bearing capacity, calc underscore allow, is the safe load per unit area that the foundation can carry without exceeding the soil strength or causing excessive settlement. It is usually derived by applying a safety factor to the ultimate bearing capacity to account for uncertainties in soil properties, load variations, and construction tolerances. Typically, a factor of safety between 2 and 3 is used. Callow equals cult FSQ underscore allow equals backslash frac Q underscore ULT FS, where FSFS equals factor of safety, usually between 2 and 3. 3. Factors affecting bearing capacity. Several factors influence the bearing capacity of foundations, including soil type, the strength of the soil x the ultimate bearing capacity. Cohesive soils, such as clay, have higher shear strength, while cohesionless soils, such as sand, rely more on friction. Foundation shape and size. The geometry of the foundation, e.g. square, rectangular, circular, can impact the distribution of load on the soil. Depth of foundation. The deeper the foundation is placed, the higher the bearing capacity, as it typically reaches stronger soil or bedrock. Water table. High groundwater levels can reduce the effective stress in the soil and lower the bearing capacity. Load type. Static loads and dynamic loads, such as those caused by wind or seismic activity, can ECT the soil's ability to resist failure. 5.3.2 Settlement of foundations. Settlement refers to the vertical displacement of a foundation caused by the loading of the structure. It is the result of the deformation or compression of the underlying soil, which may occur immediately after load application, immediate settlement, or over a longer period. Consolidation settlement. The total settlement of a foundation is the sum of all types of settlement that occur. 1. Types of settlement. Immediate settlement. This occurs due to the elastic deformation of soil immediately after load application. It is typically small and occurs quickly, often within hours or days. Consolidation settlement. This occurs in cohesive soils like clays and is time dependent. Consolidation happens when the applied load forces water out of the soil pores, causing the soil to compress over time. Differential settlement. This refers to the uneven settlement of diorite parts of a foundation due to variations in soil properties or loading conditions. Differential settlement can lead to structural damage such as cracks or tilting. Creep refers to the slow, progressive deformation of soil under a constant load, especially in fine-grained soils such as clay. 2. Settlement calculation methods. The calculation of settlement involves evaluating the amount of vertical displacement that occurs under a given load. The primary methods used to calculate settlement include elastic settlement. For granular soils, the settlement can be calculated using elastic theory, which assumes that the soil behaves elastically under the applied load. The equation for elastic settlement, delta S/delta S, is given by delta S equals QB2EI/delta S equals \frac QB squared E\I, where QQ equals applied load per unit area, kPa. BB equals width of the foundation, m. E equals modulus of elasticity of the soil, MPa. 2 equals influence factor, depending on the depth and geometry of the foundation. Consolidation settlement. For cohesive soils, consolidation settlement is calculated using Terzaghi and Peck's theory. This theory involves determining the coefficient of consolidation, CDC_V, and the time factor to estimate the time dependent settlement. The equation for consolidation settlement is SC equals QH delta sigma S_C equals \frac QH \delta sigma, where SCS_C equals consolidation settlement, QQ equals applied load per unit area, HH equals thickness of the compressible layer, delta sigma \delta sigma equals increase in vertical stress at the depth of the compressible layer. Differential settlement. Differential settlement is computed by evaluating the variation in settlement across the foundation. The maximum differential settlement is typically estimated based on the variation in soil properties beneath the foundation and load distribution. 3. Acceptable settlement limits. Settlements must be kept within acceptable limits to prevent structural damage. The total settlement should typically not exceed a value that would cause damage to the superstructure, while differential settlement should be minimized to prevent tilting or uneven stresses on the structure. Common guidelines for acceptable settlement. Total settlement for low-rise buildings, typically up to 25 millimeters. Total settlement for high-rise buildings, typically up to 50 millimeters. Differential settlement should not exceed 1/500th of the building's height, e.g. for a 10-meter high building, differential settlement should not exceed 20 millimeters. 5.3.3 Managing settlement and bearing capacity issues. To manage settlement and ensure the foundation does not exceed its bearing capacity, several techniques can be used. Improve soil compaction. Soil compaction or densification can increase the bearing capacity and reduce settlement in granular soils. Soil stabilization. Techniques such as grouting, lime stabilization, or cement mixing can improve the shear strength of weak soils and reduce settlement. Use of deep foundations. If shallow foundations cannot provide adequate bearing capacity, deep foundations such as piles or drilled shafts can transfer the load to deeper, stronger soils. Foundation design adjustments. The size, shape, and depth of the foundation can be adjusted to minimize settlement and ensure adequate bearing capacity. 5.3.4 Conclusion. The bearing capacity and settlement of a foundation are essential considerations in foundation design. Engineers must assess the soil's ability to support loads without failure, bearing capacity, and estimate the potential for vertical displacement, settlement, under the applied load. By utilizing proper design methodologies, soil testing, and engineering techniques, these factors can be carefully managed to ensure the safety and longevity of the structure. Foundation settlement and bearing capacity are interrelated, and both must be addressed to prevent structural damage and ensure the long-term performance of the building. Chapter 5. Foundation Engineering. 5.4 Advanced Techniques in Foundation Design. Advances in geotechnical engineering have led to the development of more sophisticated and efficient techniques in foundation design. These advanced methods are crucial for addressing complex challenges posed by difficult soil conditions, deep foundations, and heavy structural loads. In this section, we explore various advanced techniques in foundation design, including geotechnical improvement methods, high capacity foundations, deep foundation technologies, and specialized design methods. 5.4.1 Ground Improvement Techniques. In situations where the natural soil conditions are inadequate for supporting conventional foundations, ground improvement techniques are employed to enhance soil properties and provide a stable foundation for structures. These techniques aim to increase soil strength, reduce settlement, and control groundwater flow. 1. Soil stabilization. Soil stabilization involves modifying the soil properties to improve its engineering behavior, including increasing strength, reducing permeability, and enhancing stability. Various methods of soil stabilization include chemical stabilization, adding stabilizing agents like lime, cement, or fly ash to soil to improve its properties. This method is commonly used in fine-grained soils, such as clays, to enhance shear strength and reduce plasticity. Mechanical stabilization involves compacting the soil or mixing it with additional granular materials to increase its strength and reduce compressibility. Grouting, the injection of grout, a fluid mixture of cement, chemical agents, or resins, into soil to fill voids, bind particles together, and increase shear strength. Permeation grouting is used to reduce permeability, while compaction grouting is used to increase soil density and strength. 2. Vibrocompaction. Vibrocompaction is used in granular soils, such as sands, to densify the soil by using a vibrating probe to rearrange the particles and improve the soil's compaction. This technique is particularly effective for improving the bearing capacity and reducing settlement in loose or non-cohesive soils. 3. Deep soil mixing (DSM). Deep soil mixing involves injecting a binder material into the ground while simultaneously mixing it with the surrounding soil to create stronger, more stable soil columns. This technique is used for improving the bearing capacity and reducing settlement in weak soils. 4. Geosynthetics and reinforcement. The use of geosynthetics, such as geotextiles, geogrids, and geomembranes, helps to reinforce weak or loose soils, prevent erosion, and reduce settlement. Geosynthetics are typically used in applications like slope stabilization, retaining walls, and subgrade reinforcement for pavements. 5.4.2 High-capacity foundations. High-capacity foundations are designed to support structures with large loads or those built on soft or weak soils. These foundations require innovative design methods and advanced materials to achieve high load carrying capacity while minimizing settlement. 1. Raft foundations. A raft foundation or mat foundation is a large, thick concrete slab that spreads the loads of a structure over a wide area. It is used when the soil has low bearing capacity or when settlement must be minimized. Raft foundations can be combined with soil improvement techniques to enhance performance. Reinforced rafts. These are reinforced with steel mesh or steel bars to enhance their load carrying capacity and prevent cracking under large loads. Floating rafts. Floating raft foundations are used in soft soils, and they are designed to displace their own weight in order to minimize settlement. 2. Pile soil interaction models. In designing pile foundations, advanced pile soil interaction models are used to predict the behavior of the pile under various loading conditions. These models take into account factors such as soil nonlinearity, the variation in soil resistance with increasing load. Group EX, the interaction between multiple piles in a foundation which may reduce individual pile capacity. Dynamic loading, piles subjected to seismic or vibrational forces requiring dynamic analysis for predicting response. Numerical methods, including finite element analysis (FEA), are used to model pile soil interactions more accurately. 3. Geotechnical monitoring and instrumentation. Advanced monitoring technologies are now used to measure and assess the performance of high-capacity foundations in real time. Instruments such as settlement gauges, strain gauges, and piezometers are installed in the foundation and surrounding soil to monitor settlement, lateral movement, and pore pressure during construction and throughout the life of the structure. Real-time data from these instruments helps in making adjustments to the foundation, design, and mitigating potential issues. 5.4.3 Deep Foundation Technologies. In areas where shallow foundations are insufficient due to weak soils, high water tables, or deep bedrock, deep foundations are employed. These foundations transfer loads to deeper, more stable soil or rock layers. Recent advances in deep foundation technologies have provided more efficient and cost-effective solutions. 1. Screw piles and auger cast piles. Screw piles and auger cast piles are increasingly used as alternatives to traditional driven piles. They are installed using a rotating helical screw or auger, which minimizes soil disturbance and reduces installation time. These piles are particularly beneficial in sensitive environments where vibrations from pile driving must be minimized. Screw piles. These are steel piles with helical threads that are screwed into the ground, allowing quick installation and high load-bearing capacity. Auger cast piles. These piles are installed by rotating an auger into the ground to create a hole, which is then filled with concrete. This method is ideal for cohesive soils where pile driving would be difficult. 2. Micropiles. Micropiles, also known as mini piles, are small diameter piles, typically less than 300 millimeters in diameter, that are drilled and grouted into the soil. Micropiles are used in areas with limited access or when traditional pile driving is not feasible. They are commonly used for retrofitting existing structures or in challenging soil conditions such as rock or dense gravel. 3. Hybrid pile foundations. Hybrid foundations combine different foundation types to optimize performance in varying soil conditions. For example, end-bearing piles can be used in deep, strong layers of soil or rock, while friction piles can be used in shallower, weaker soils. Hybrid foundation systems can provide higher load capacities and minimize settlement across large structures. 5.4.4 Specialized Design Methods. 1. Seismic foundation design. In seismic regions, special considerations must be made for foundations to ensure that they can withstand earthquake-induced forces. Advanced seismic design methods include dynamic analysis. This analysis involves evaluating the dynamic response of the structure and foundation to seismic loads, using methods such as finite element modeling or spectral analysis. Seismic isolation. Seismic isolation devices, such as base isolators, are used to decouple the structure from ground motion, reducing the forces transmitted to the foundation. Liquefaction mitigation. In areas prone to soil liquefaction, techniques like soil densification or the installation of deep foundations are used to reduce the risk of liquefaction during an earthquake. 2. Floating foundations. In some conditions, such as in very soft soils or locations with high groundwater levels, floating foundations are used. These foundations are designed to distribute the load of the structure evenly across a large area, reducing the risk of torrential settlement. Floating foundations are often used for buildings and structures on marshy or flood-prone land. 3. Tuned mass dampers (TMDs). Tuned mass dampers are installed in the foundation or structure to reduce oscillations caused by wind, seismic activity, or other dynamic forces. These devices help to control vibrations and prevent structural damage. They are commonly used in high-rise buildings and bridges. 5.4.5 Conclusion. The advanced techniques in foundation design are engineers' powerful tools to address complex challenges posed by difficult soil conditions, large structures, and dynamic loads. By incorporating ground improvement methods, high-capacity foundations, deep foundation technologies, and specialized design methods, engineers can ensure the safety, stability, and longevity of structures in a variety of environments. As geotechnical technology continues to advance, new materials, computational models, and construction techniques will further enhance the ability to design foundations that can withstand increasingly demanding conditions. Chapter 5. Foundation Engineering. 5.5 Foundation Performance under Dynamic Loading. Dynamic loading refers to forces or loads that vary with time, such as those induced by earthquakes, wind, machinery vibrations, ic, or seismic events. Foundations must be designed to withstand dynamic forces to ensure the stability and safety of the structures they support. This section explores the effects of dynamic loading on foundations, the methods for assessing foundation performance under such loads, and techniques for mitigating potential issues. 5.5.1 Types of dynamic loads on foundations. Dynamic loads can take various forms depending on the nature of the forces acting on the structure. Some common types of dynamic loads include seismic loads. Earthquakes generate seismic waves that cause ground motion, which is transmitted to the foundation and structure. These forces can lead to settlement, lateral movement, and structural deformation if the foundation is not adequately designed. Wind loads. High winds, particularly in coastal or hurricane-prone areas, can exert significant lateral loads on tall structures. The foundation must be able to resist these lateral forces and prevent overturning. Vibration from machinery. Foundations supporting vibrating equipment such as turbines, compressors, or heavy machinery, are subjected to repetitive dynamic forces. These vibrations can lead to settlement, fatigue, or resonance if not properly addressed in the foundation design. TRA-IC and impact loads. Foundations supporting transportation infrastructure, such as bridges, roads, or railways, are subjected to dynamic loads from moving vehicles, trains, or wind forces. These loads can cause cyclic loading EX, leading to potential fatigue and wear. Tidal and wave forces. In coastal regions, foundations supporting shore platforms or buildings near water bodies must be designed to resist the dynamic forces of waves, tides, and water currents. 5.5.2 Dynamic soil structure interaction. The behavior of foundations under dynamic loading is influenced by the interaction between the soil and the structure. The response of the foundation depends on various factors such as the steepness and damping characteristics of both the soil and the structure. This interaction is called soil structure interaction, SSI. 1. Dynamic characteristics of soil. The response of the soil to dynamic loads is typically characterized by its dynamic steepness and damping. These properties vary with soil type, depth, and loading frequency. Dynamic steepness represents the ability of the soil to resist deformation under dynamic loading. The steepness of the soil can vary with the frequency of loading, with softer soils exhibiting lower steepness at higher frequencies. Damping. Damping refers to the soil's ability to dissipate energy during dynamic loading. Materials like clay tend to have higher damping ratios than granular soils, such as sand. 2. Foundation response to dynamic loads. The foundation's ability to transfer dynamic loads to the soil and the subsequent response of the soil are influenced by the foundation's type and geometry. The response can be divided into two primary types. Vertical response involves the foundation settling or vibrating in response to vertical dynamic loads, such as from seismic or machinery-induced forces. Settlements can be elastic, recoverable, or inelastic, permanent. Lateral response involves horizontal movements of the foundation, typically in response to wind, seismic, or TRA-IC-induced forces. Lateral displacement can result in tilting, slippage, or shear failure in the soil. 3. EX of dynamic loading on foundation performance. Dynamic loading can cause several significant EX on foundation performance, including excessive settlement. Foundation settlement due to dynamic loading can be problematic, especially when the settlement is uneven or occurs too rapidly. This can ECT the structural integrity of the building and cause misalignment of utilities or structural components. Liquefaction. In loose, saturated soils, strong dynamic loading, such as an earthquake, can cause liquefaction, a phenomenon where the soil temporarily loses its strength and behaves like a liquid. This can lead to foundation failure and displacement. Resonance. If the frequency of dynamic loading matches the natural frequency of the foundation or structure, resonance can occur, leading to amplified vibrations that can cause significant damage. Fatigue and wear. Repetitive dynamic loading, such as from machinery or TRA-IC, can lead to fatigue in foundation materials, increasing the risk of cracking, deformation, and eventual failure over time. 5.5.3 Dynamic Analysis of Foundations. To ensure foundation performance under dynamic loading, dynamic analysis is often performed. This analysis assesses the behavior of foundations under dynamic loads and predicts their performance under various conditions. Dynamic analysis methods include 1. Equivalent static method. This simplified approach involves converting the dynamic load into an equivalent static load, typically using a response spectrum or a dynamic load factor. It provides a rough estimate of the foundation response under dynamic loading, but does not capture all the complexities of soil structure interaction. 2. Time history analysis. Time history analysis is a more detailed method where the actual time varying nature of the dynamic load, such as earthquake ground motion or machine vibration, is considered. It involves solving the equations of motion for the structure and foundation system, taking into account the time-dependent nature of the forces. 3. Response spectrum analysis. Response spectrum analysis is a common method for seismic design that involves calculating the peak responses of a foundation to dynamic loads using a predetermined spectral curve. This method is used to estimate the maximum response of the system at different vibration frequencies. 4. Finite element analysis (FEA). Finite element analysis (FEA) is a computational technique used to simulate the dynamic response of foundations and structures under dynamic loads. FEA divides the foundation and soil into discrete elements, allowing for detailed analysis of the soil structure interaction. This method is particularly useful for complex foundation systems and large-scale projects. 5. Dynamic soil structure interaction (SSI) analysis. SSI analysis evaluates the interaction between the foundation and the surrounding soil under dynamic loading. This analysis considers the dynamic characteristics of both the structure and the soil and is essential in cases where the foundation is in soft or heterogeneous soils. 5.5.4 Mitigation strategies for dynamic loading. Several techniques are available to mitigate the effects of dynamic loading on foundations and structures. These techniques aim to reduce the amplitude of vibrations, prevent soil failure, and minimize settlement under dynamic loads. 1. Foundation dampers. Foundation dampers are devices installed in the foundation system to absorb and dissipate the energy generated by dynamic loads. Viscous dampers, friction dampers, and tuned mass dampers, TMDs, can be used to reduce the impact of vibrations and seismic forces on the foundation. 2. Seismic base isolation. Seismic base isolation involves installing flexible bearings or isolators between the foundation and the structure. These devices decouple the structure from the ground motion, reducing the seismic forces transmitted to the building. This method is especially effective in seismic-prone areas. 3. Soil improvement for liquefaction mitigation. In areas where liquefaction is a concern, soil improvement techniques such as vibrocompaction, grouting, or the installation of drainage systems can be used to enhance soil strength and prevent liquefaction during seismic events. 4. Use of deep foundations. In areas prone to settlement or liquefaction, deep foundations such as piles or drilled shafts may be used to transfer loads to deeper, more stable soil or rock layers. Pile foundations can help reduce the settlement induced by dynamic loads and provide greater stability in unstable soils. 5. Vibration isolation for machinery foundations. For foundations supporting vibrating machinery, vibration isolation systems can be employed to minimize the transmission of vibrations to the surrounding soil and structure. Techniques such as rubber bearings, spring dampers, and floating slab foundations can be used to reduce vibration amplitudes and prevent fatigue damage. 5.5.5 Conclusion. Foundation performance under dynamic loading is a critical consideration in ensuring the safety and longevity of structures. Dynamic loads, whether from seismic activity, wind, machinery, or TRA-IC, can significantly ECT foundation behavior, leading to settlement, liquefaction, or fatigue. By understanding soil structure interaction, conducting dynamic analysis, and applying mitigation strategies such as damping, isolation, and soil improvement, engineers can design foundations that effectively resist dynamic forces and provide safe and stable support for structures. With the advancement of computational modeling and dynamic testing methods, the ability to predict and mitigate the effects of dynamic loading on foundations continues to improve, ensuring the resilience of infrastructure in an increasingly dynamic world. Chapter 5. Foundation Engineering. 5.6 Case Studies in Foundation Failures and Successes. Case studies are invaluable in understanding the real-world challenges and solutions in foundation engineering. By examining past foundation failures and successes, engineers can learn important lessons about design, material selection, construction techniques, and the importance of thorough site investigation. This section explores a range of case studies that highlight both foundation failures and successes, providing insights into common pitfalls and best practices in the field. 5.6.1 Case Studies of Foundation Failures. Foundation failures can occur due to various reasons such as poor design, inadequate soil conditions, material flaws, construction errors, or unforeseen environmental factors. Below are a few notable examples of foundation failures and the lessons learned from each. 1. The Leaning Tower of Pisa, Italy. One of the most famous foundation failures in history is the Leaning Tower of Pisa, which began tilting shortly after its construction started in 1173. The tower's foundation was built on weak, soft clay and sand, which could not support the weight of the tower. Over the centuries, the tilting continued due to uneven settlement of the foundation. Lessons learned. Soil conditions are critical. A thorough geotechnical investigation should always be conducted to assess the soil conditions before beginning construction, particularly in areas with soft or unstable soils. Foundation design considerations. A foundation must be designed to account for long-term settlement and load-bearing capacity of the soil. The use of deep foundations or soil improvement may have mitigated the issue. 2. The Lotus Riverside Complex, Shanghai, China. In 2009, a residential complex in Shanghai experienced a major foundation failure when an entire building collapsed due to inadequate foundation design. The building was constructed on soft, compressible clay, and the foundation was not designed to accommodate the excessive settlement. This resulted in the collapse of the building. Though fortunately, it occurred before residents had moved in. Lessons learned. Soil improvement is essential. In regions with soft or compressible soils, it is crucial to use soil stabilization techniques, e.g., grouting, vibrocompaction, or to install deep foundations like piles to transfer loads to deeper, more stable layers. Site investigation and monitoring. A detailed site investigation, including soil testing, should be conducted before construction. Additionally, continuous monitoring of foundation performance can help detect issues early. 3. The Hyatt Regency Hotel collapse, Kansas City, USA. In 1981, the Hyatt Regency Hotel in Kansas City suffered a catastrophic collapse of its atrium walkway, resulting in 114 deaths. The collapse was primarily due to a design flaw in the suspension system of the walkway's hanging structure, which was supported by columns embedded in the foundation. The failure of the system was traced to incorrect calculations, and the inadequate design of the foundation system contributed to the failure. Lessons learned. Rigorous design and engineering reviews. Proper review of structural and foundation designs is critical to prevent failure. In this case, a lack of coordination between the design and construction teams led to the use of a foundation system that could not withstand the loads. Comprehensive load analysis. Foundations should be designed to account for both static and dynamic loads, as well as safety margins. Engineering calculations need to be verified through detailed analysis and review. For the St. Francis Dam collapse, California, USA. In 1928, the St. Francis Dam in California failed catastrophically, resulting in the deaths of more than 400 people. The dam's foundation was built on poorly consolidated and water-saturated rock, which led to the eventual failure of the structure. The foundation design did not account for the seepage and internal erosion caused by water flowing through the rock beneath the dam. Lessons learned. Geotechnical investigations are critical for dam foundations. Comprehensive subsurface investigations, including testing for permeability, shear strength, and consolidation characteristics, should be conducted when designing foundations for dams or other large structures. Consideration of water-related forces, dams, and other water-related structures should be designed with careful consideration of seepage, water pressures, and erosion risks. It is essential to implement adequate drainage and waterproofing measures. 5.6.2 Case studies of successful foundation design. While foundation failures are often widely reported, there are also many examples of successful foundation design and construction. Below are a few examples where innovative techniques and sound engineering practices led to successful foundation projects. 1. The Burj Khalifa, Dubai, UAE. The Burj Khalifa, the world's tallest building, stands on a foundation that is an impressive feat of geotechnical engineering. Due to the extremely soft soil conditions in Dubai, the foundation consists of a large reinforced concrete mat, raft foundation, and over 190 board reinforced concrete piles that reach 50 meters below the ground. Success factors. Innovative foundation design. The raft foundation distributes the building's load across a large area, while the deep piles ensure that the building is anchored to more stable rock layers. Geotechnical expertise. Detailed soil investigations, including boreholes and lab testing, were performed to ensure that the foundation was designed to withstand the massive loads of the structure. Risk mitigation. The foundation design accounted for potential soil settlement, ensuring that the building would remain stable over time. 2. The Millau Viaduct, Millau, France. The Millau Viaduct is a cable-stayed bridge that spans the Tarn River in southern France. It stands as one of the tallest bridges in the world, with several of its piers reaching over 240 meters in height. The foundation design for the piers included the use of deep board piles and extensive geotechnical studies to ensure that the bridge could withstand seismic forces, high winds, and the weight of the bridge itself. Success factors: deep foundations for tall piers. The use of deep bored piles ensured that the foundation could support the immense weight of the piers, even in rocky, challenging soil conditions. Advanced structural and geotechnical design. The project utilized cutting-edge engineering tools and computational modeling to simulate the behavior of the foundation under dynamic loads such as seismic forces and wind. Environmental and geotechnical considerations. The foundation design incorporated methods to minimize environmental disruption and preserve the stability of the surrounding area. 3. The Oslo Opera House, Oslo, Norway. The foundation design for the Oslo Opera House was complex due to the site's location on soft clay and its proximity to water. The foundation was designed as a combination of a mat foundation and board piles. In addition, the design included soil improvement techniques to enhance the strength and stability of the soft clay beneath the foundation. Success factors: innovative site-specific solutions. The combination of mat foundations and deep piles ensured that the building was anchored to stable, firm soil layers, even though the surrounding site conditions were challenging. Use of soil improvement. Soil stabilization techniques were used to reduce the settlement of the soft clay and improve the bearing capacity beneath the foundation. Sustainability considerations. The project included measures to minimize disruption to the local ecosystem, such as designing a foundation system that minimized the impact on nearby water bodies. 4. The Sydney Opera House, Sydney, Australia. The Sydney Opera House, known for its iconic design, was built on a foundation that overcame significant challenges related to its location on reclaimed land and coastal soil conditions. The foundation design utilized deep piers to anchor the building to more stable rock beneath the soft soils. Success factors: innovative foundation design. Deep piers were used to transfer the loads of the structure to stable rock layers beneath the shallow, unstable soils. Adaptation to site conditions. The foundation design was adapted to the challenging site conditions, including the potential for settlement and soil movement due to the reclaimed land. Long-term durability. The foundation system was designed to minimize the effects of settlement and allow for long-term performance, contributing to the building's longevity. 5.6.3 Conclusion. The case studies of both foundation failures and successes provide invaluable lessons in foundation engineering. Failures often result from inadequate site investigations, poor material selection, inadequate design, or a lack of attention to environmental factors, while successful foundations typically result from thorough geotechnical investigations. Innovative design. and careful consideration of site-specific conditions. By studying these cases, engineers can continue to improve foundation design, leading to safer and more reliable structures. Thanks for watching. We hope you found the content informative and valuable. The link to part 3 of this video will be embedded in the description below, so be sure to check it out. If you enjoyed the video, please click like and share it with others. And if you haven't subscribed to our channel yet, make sure to hit the subscribe button now so you don't miss out on future content.